Today we're visualizing how language models understand words using something called vector embeddings. So imagine this. We start with a simple 2D space, just x and y coordinates. Now, instead of plotting numbers, we plot words. First, we place the word dog as a point in this space with its own unique coordinates. In this world, a word isn't just text anymore, it's a position. Next, we add another word, pug. Since a pug is a type of dog, its point appears very close to dog. Small distance means similar meaning. Now we place cat. It's still an animal, but different from a dog, so it appears farther away. But near cat, we add lion. And just like dog and pug, cat and lion close together. These form clusters, groups of related meanings. We can even go further. Add words like king, queen, and prince. They form another cluster, royalty, far from animals, but close to each other. So, what does this show? Words with similar meanings stay close. Different meanings create distance. This is how models understand relationships through geometry. But here's the catch. This 2D space is just for visualization. In reality, models like GPT-2 don't use 2 dimensions. They use 768 dimensions. That means every word, like apple, becomes a point in a 768-dimensional space. Sounds crazy, but that's where meaning lives. So in the end, language becomes math. Meaning becomes distance, and that's how AI understands words.
Okay, so what's up, bad boys and girls? Welcome to this video, and let me just give you a whole overview of what we are going to do today. So in the previous video, we discussed how we can convert an word into a byte sequence, basically a token ID. We discussed how we use byte pair encoder and merging methods to create our own vocabulary for our LLM. Now, using that vocabulary, we are going to use the ID we get from that vocabulary, and for a sentence, apple are healthy, you can see each element is getting a token ID, each element is getting a byte encoded token ID. So this apple is encoded as a byte using the vocabulary of our byte pair encoder. Okay, that must be enough. If you want to go in detail, I have made a detailed video about this, and we are going to discuss some parts of it, some necessary parts of this process in this video as well. But mostly we will deal with this token ID, and we will use this token ID to pass through our embedding weights and look inside our embedding table to generate a 768 dimension rich embedding, and we also add a position to it. So without wasting your time, let's just get straight into it and understand how this all process works.
Now let's step inside a model like GPT-2 and see how it understands text. We start with a simple sentence. The apple fell from the tree. But machines don't understand words directly. They first need to convert them into tokens. So step 1 is tokenization, using something called a byte pair encoder. Let's zoom in on a single word, apple. This word is sent into the byte pair encoder, where it is first broken down into smaller pieces, individual characters, A, P, L, E. Now comes the interesting part. The encoder starts merging these characters step by step based on patterns it has learned from large data sets. So instead of keeping them separate, it gradually combines them back together until it forms the complete word, apple. Once the final token is formed, the model looks it up in its vocabulary. Every token in this vocabulary has a unique number called a token ID. And for apple, that ID might be something like 729. So just like that, a simple word is transformed into a number ready to be processed by the model. Now that we've converted the word apple into the token ID 729, what happens next? This is where many people get confused. That number, 729, is not a vector. It's just an index. Think of it like a position in a table, not the actual meaning. In models like GPT-2, we use this token ID to look inside something called the embedding matrix. This matrix is a large table of learned vectors, where each row corresponds to a token. So when we take token ID 729, we simply go to row number 1729 and select that vector. That's it, no multiplication with the number itself. But technically, what's happening behind the scenes is even more interesting. The token ID is first represented as a one-hot vector, a vector full of zeros with a single one at position 1729. This one-hot vector is then multiplied with the embedding matrix. And what does that do? It simply selects the correct row, like a smart lookup operation. So instead of computing something complex, we're just retrieving a pre-learned vector. And this vector, typically something like 768 dimensions, is the actual embedding of the word. It captures meaning, context, and relationships, all learned from massive amounts of data. So remember the key idea. We don't multiply the token ID, we use it to look up the embedding from word to token to vector. This is how meaning enters the model.
Okay, so let's also learn how does the embeddings are learned in LLM. So we just used embeddings to get our vector for a token, but how are they learned? So the first step is we make the model to predict a vector. We ask the model to predict a word based on the token ID. So we pass the token inside the model, and model creates different outputs for that token. It basically checks what could be the output for that token. In this example, Apple has been predicted as the 62% accuracy, cat has been predicted as 18% accuracy. So it gives you give the token ID and it predicts the output. So the target word was Apple, but our model right now predicted 62%. So it's still not sure that for this token ID, the word in the vocabulary should be Apple. So what we do, we introduce a loss function. A loss function is just basically a punishment that we give to the model for predicting something wrong, something that was not desired. So high loss equals to model was less confident and must learn more. Now how do we use this loss? We use backpropagation. Basically, after the model's prediction, we find out that this prediction was wrong, and what we do, we try to update the weights. We try to update the embeddings in the weight matrix using backpropagation. So it's basically a backward pass. We are updating the weights based on our loss that you were not able to find the correct answer. So this much you imagined wrong, this much of your probability was wrong. So update your vectors, update your embeddings such that you predict the right thing. Now the weights are updated. Basically, we go inside the model embeddings and we search for the row 1729. That was the vocabulary for predicting the word apple. Now we update this embedding. We update the weights of this embedding. We change them based on a loss. And then we make it again predict the vector. We make it again predict the word. And we keep doing this multiple times till the model is totally confident in predicting that for token 1729 the output should be the word apple. And this is how the model learns input embeddings, and it is able to predict, it is able to search for a word in its vocabulary based on a token. So weights are updated to make the correct predictions more likely next time. Forward pass, first we do a forward pass, then we do a backward pass, and we update the weight based on the loss. Over millions of training steps, embeddings capture the semantic meaning at the end.
Let's understand how we give words their position in a sentence. Imagine the sentence, apple is sweet. Here, the word apple is at position 0. Now, we already have an embedding for the word apple, but that only captures its meaning. To tell the model where the word appears, we need a positional embedding, and it must have the same size, 768 dimensions, so we can combine them later. So how do we create this positional embedding? We fill a 768-dimensional vector using sine and cosine functions. For even index dimensions, we use sine. For odd index dimensions, we use cosine. Each value is calculated using the position and the dimension index. Since apple is at position 0, sine of 0 gives us 0 for all even dimensions, and cosine of 0 gives us 1 for all odd dimensions. Now we have our positional embedding vector. The next step is simple. We add this positional embedding to the word embedding of apple. This addition combines both pieces of information, what the word means and where it appears in the sentence. This final combined vector is what we pass into the model, and that's how positional embeddings work. By using sine and cosine patterns and adding them to word embeddings, we give the model a sense of order in language.
Okay guys, thanks for watching this video. And in the end, we have now completely understood how we can convert any token ID into an embedding and add positional encoding to it. And this will be ready for self-attention once we apply a normalization step on this. So to understand how normalization works, please watch my next video, and thanks for your time.